Okay. So we have this ledger where there are people posting assertions together with short proofs that support the assertions they make. For example, if I'm claiming that I know the secret key of a corresponding public key that is sitting there on the blockchain, I don't want to, of course, give the secret key. So we want to be able to prove certain claims in zero knowledge, and these proofs are on the blockchain, so we also want it to be short and efficiently verifiable. And this is where zkSNARKs are very important. So we have seen a lot of zero knowledge proof in the past 2 talks, so I'll keep this very brief just to have the setting here. So we have a prover and a verifier. There is a public function and a claimed output, and the prover is also in possession of a private input that we call a witness, and the prover claims that he knows this W such that f of W is Y. And the prover and the verifier interact, and at the end of it, the verifier chooses to either accept or reject depending on whether she's convinced or not. And we have this completeness property that says that an honest prover who actually knows such a W should be able to convince the verifier of a true statement. And the property of soundness says that if the prover is cheating, then no matter what he does, he should not be able to convince Alice about a statement that is not true. And now the zero knowledge property says that if the verifier is cheating, she cannot learn anything more than the validity of the statement itself. And for applications on the blockchain, we need this additional property that is called succinctness, which is essentially about the following. If the prover is claiming something about a very expensive computation, how efficient can the verifier be? Should the verifier expend as much resources as it takes to compute the function itself to be able to convince or not? So succinctness, for the purposes of this talk, is a proof system where the communication is logarithmic in the size of the statement and the witness. We can also think of succinctness of the verification, where the verification expends resources less than computing f itself. So a zero knowledge succinct proof, you can see, is a very powerful tool that allows one to prove things about the integrity of a computation in a privacy preserving way, and naturally it has many applications in the blockchain. And it was constructed by Killian in the early 90s. Unfortunately, this came with 2 downsides that doesn't already allow us to use it for blockchain applications. The first one being it was interactive, meaning it cannot be posted on the blockchain. So if a prover wanted to convince everybody in the world about a certain assumption, that would mean the prover had to interact with everybody, and that's not possible. And second, it had poor concrete efficiency, which means it relied on things like PCP. These are the objects that you all talked about yesterday. And even though they are asymptotically succinct, concrete efficiency is poor, and it doesn't lend itself to applications for blockchain protocols. And what about interactivity? So what we really want is a non-interactive zero knowledge proof to be able to just post it on the blockchain. And the setting is the following, where the prover sends a one-shot message to the verifier. And depending on this proof and the public function and the public output, the verifier decides to accept or not. So now we are ready to define what a zkSNARK is. First of all, it is succinct. It is non-interactive. It is an argument, not an argument of this kind, but an argument is a proof system where the soundness holds only against a computationally bounded prover. Moreover, it's an argument of knowledge, which means that if a prover convinces a verifier, there exists an algorithm called an extractor that can interact with the prover and spit out a witness. And it's also zero knowledge. So for the rest of the talk, I will not make this technical distinction between arguments and proofs, and I'll say proofs when I really mean arguments. And when we look at constructions, I will not focus on zero knowledge because more often than not, it is easy to achieve and all the hard work is for soundness. Okay, so the first zkSNARK construction was Micali's in '94. Which is basically in the random oracle model. So we have this hash function that behaves ideally, and now we can have a zkSNARK where the proof is short and can be succinct, and it can be posted on the ledger because it's non-interactive. So why are we not done yet? Because essentially this construction is where the prover is thinking about Killian's construction in the head, making it non-interactive and shipping it off to the verifier. So it still has all the downsides of Killian's construction, which means it is still too large in a concrete sense to be put on the blockchain. So we went on a quest for zkSNARKs, and a sort of second era was started by this result of Gentry and Wicks, which was really about assumptions to construct zkSNARKs. And the Gentry-Wicks result is basically a negative result, which says that we cannot base zkSNARKs on standard assumptions in a black box way, that is, falsifiable assumptions. They don't rule out static soundness, but because we care about adaptive soundness for the applications that I'll talk about, I will again not make this distinction. And after the Gentry-Wicks results, there were a bunch of positive results that actually made these non-falsifiable assumptions called knowledge assumptions. And we have many constructions based on PCPs and efficient constructions that are based on linear PCPs, which also we heard a little bit about yesterday. So for the rest of the talk, we will look at one such construction, which is based on a linear-only encoding scheme. So what is the setting? The setting is the same as before. We have a prover and a verifier, and we want a non-interactive one-shot short proof. But now, additionally, we have some help. So we have some initial help, which we call a setup. So we're going to fix the function f that we want to prove statements about. And the setup is going to toss some coins and output a proving key and a verification key. So both of them are going to be public, but the proving key is large as the size of the circuit that we want to prove statements about, and the verification key is going to be short. And now the instances can come in, and the prover can use this proving key to prove as many statements as he wants about this function f. The verifier can use the small verification key and the small proof to check whether this is true or not. And recent developments show how to make this proof really, really small, which gives us about 3 to 6 group elements, which in practice is a few 100 bytes that can be posted on the blockchain with almost no overhead. And the verifier is also very efficient. In the most efficient constructions we know today, the verifier has to compute 3 pairings, and the number of exponentiations that depends on the length of the public output. Okay, so there are a bunch of variants based on this setting here, which depends on, does the setup depend on f? Like, is the setup doing something specific about the function that we want to prove or not? Is the setup cheap or expensive? That is the setup as expensive as the statement that we're trying to prove? And is there secret or public randomness involved in the setup? And who is this proof for? Who is going to be convinced? Is it for everybody in the world, or is it for a designated party who holds the corresponding secret key for some public key? So mostly we will focus on what are called preprocessing SNARKs, which have a setup that depends on f. So we have an expensive setup. There are secret coins involved in the setup, and it achieves public verifiability. So this will sort of be our journey for the rest of the talk. We will begin with a computation. We will represent it as an arithmetic circuit over a field, then convert it into a representation that's called a quadratic arithmetic program, and from there we will go into zkSNARK. So this is reinterpreted as a linear PCP, but this is also something you all told us about yesterday. Okay, so we have a computation that we want to prove something about. We represent this computation f over a field where w is the witness, and we want to say f of w is y, where y is public. So the arithmetic circuit C is over a large finite field. And we look at the vector A, which represents the sort of the extended witness, which is the values on all the intermediate wires. And this is equivalent to saying there exists these assignment to all the internal values of the internal wire values such that the circuit accepts with these internal wire values. And these addition and multiplication gates of the arithmetic circuit C gives us a system of constraints. And we want to encode these constraints in a way such that it is easy to construct a zkSNARK. Okay, so let's look at what the constraint system should be like. So let's say we have, so I have shown one addition and one multiplication gate here, and addition gates are usually for free, so let's just focus on the multiplication gate. Okay, so let's look at how to convert a circuit to what is called QAP. A QAP is a characterization of NP and it's useful because it lends itself to easy construction of zkSNARKs. Okay, so we have the circuit. I have labeled this multiplication gate as G, and we have all these internal wire values labeled by A's. To convert this into a QAP, we do the following, and I'll tell you later why it's a good idea. So for every multiplication gate in the circuit here, which I'm calling G, we're going to pick what we call a root that corresponds to this gate, represented by RG for every multiplication gate. And we're going to construct what we call a target polynomial that is basically defined to have all these RGs as roots. So it has degree that is as big as the number of multiplication gates in the circuit. And now we want to construct some sets of polynomials to encode the values corresponding to the input and output wire values of this gate. And how do we do this? So we have three sets of polynomials that I'm going to call V, W, and Y throughout. And at a high level, we want to think of the V polynomials as encoding the left input of a multiplication gate. What do I mean? So the ith V polynomial has Rg as a root if the ith wire is not left input to the gate G. So Vi of Rg is 1 if the ith wire is left input to gate G. Again, remember each Rg corresponds to a multiplication gate G, and I's are indices that are wire indices. So we have all these wires labeled from 1 to m, and there are as many polynomials in each of these sets as the number of wires in the circuit. And now I want to encode all the left input wires of a multiplication gate by V polynomials by defining them this way. And the W polynomials are going to encode the right input of a gate, and again we say Wi at Rg is 1 only if the ith wire is right input to gate G, otherwise it is 0. And the Y polynomials encode the output wire of a multiplication gate, and again Yi of Rg is 1 if the ith wire is the output wire of gate G. So if I label the input and output wires of the multiplication gate here by 1, 2, and 3, what this means is V1 of Rg is 1, rest of it is 0, W2 of Rg is 1, and Y3 of Rg is 1. Right, so why did we do this? So now what is a QAP? A QAP is all these sets of polynomials together with the target polynomial, and we say that this QAP computes the circuit F if the following holds, that is A1 to AN and AK to AM are valid assignments to the input and output wires of the circuit if and only if there exist intermediate A values, that is AN plus 1 to AK minus 1, such that the polynomial expression here, the target polynomial T, divides this polynomial expression here. So let's go over this a little slowly. So what is this polynomial P? The polynomial P is a linear combination of the V polynomials times a linear combination of the W polynomials minus a linear combination of the Y polynomials. And notice this is the same linear combination in all of these, the same coefficients in all the linear combinations. And now if we say the target polynomial divides this polynomial P, that means we have this equality modulo T, And what does this mean? If we look at what happens at a particular root G, that is the root that corresponds to the gate G, which is Rg, at Rg, because of the way we define Vi and Wi and Yi polynomials, this basically gives us what corresponds to the constraint of a multiplication gate. And when there are many gates using CRT, this decomposes into individual quadratic constraints. So what we have done is pack all these constraints into sort of one constraint. Yeah. Okay. So now we have represented this circuit, we have represented the constraints of the circuit as a question about divisibility of polynomials. And we also have this nice polynomial H, the quotient polynomial that serves as the witness, which is guaranteed to exist. And what we can do now is sort of check that this equation holds by drawing an element randomly from the field and checking that this equation holds at that point. And assuming that the field is large enough compared to the degree of the polynomials, we have high soundness in this test. Okay, so now we have a QAP representation of an arithmetic circuit, and that actually gave us something. We know how to check all the gate constraints of a circuit using just one test, but we didn't do any cryptography until now. So the way, one idea to do this is to use additively homomorphic encoding and then check this quadratic equation underneath the encoding. And to achieve publicly verifiable zkSNARKs, this encoding is typically exponentiation in a bilinear group. So if you want to encode a value, you put it in the exponent of a generator that generates a group that admits a bilinear map. And to check this quadratic equation, we know that bilinear maps allows us to do one multiplication in the exponent, and that allows us to make this quadratic test once. And we can get designated verifier SNARKs if we have homomorphic encodings that are designated verifier. Okay, so just to sort of put things together, we have this setup phase where all the polynomials of the QAP are encoded. And how are they encoded? They are all evaluated at a secret point and encoded by putting them in the exponent. So G is a generator of a bilinear group. S is secret from the field that is drawn during the setup phase. All the polynomials are evaluated at that secret point and they are encoded, and this gives us the long CRS. And now to use this to compute a proof, the prover who knows a satisfying assignment can compute all the intermediate wire values. And if you recall, these values were exactly the coefficients used in the linear combination. So now the prover can actually compute what are called proof elements by simply computing a polynomial V as a linear combination of these polynomials. And the prover can indeed do this even though they are encoded because of the homomorphism that exponentiation allows. So the prover can compute V of S in the exponent by computing a linear combination of AI and Vi of S. And similarly, the prover can also compute an encoding of W, Y, and the quotient polynomial that is guaranteed to exist if this is indeed a satisfying assignment. Recall T here, that is used to compute the quotient polynomial, is the target polynomial of the QAP. And now the verifier needs to check divisibility, and that can indeed be done using the bilinear map by using three pairings here. And this equation is basically checking that V times W minus Y is T times H, which is exactly the divisibility condition that the QAP gave us. Okay. So now that we have succinct SNARKs that actually give us very small proofs, let's look at some applications to blockchain. These kind of preprocessing based zkSNARKs are what underlies Zcash. So what Zcash does is basically look at transactions and encrypt them and then give out proofs saying that these transactions are indeed valid. So at a very, very high level, a transaction basically consists of a bunch of ciphertexts. It basically encodes a sender address, a recipient address, an amount, and with every transaction, there is a proof that attests to the validity of this transaction. So this proof basically says, here are 3 ciphertexts, and underneath these ciphertexts are values that contain a valid sender address, a recipient address, and a transfer amount, and this transfer amount is indeed valid. That is, it has not been spent before and I'm not double spending. There is a lot under the hood because this doesn't already work and there are more ideas necessary to make Zcash work. There are serial numbers for every coin, and coin commitments are stored in a Merkle tree, and the root of the Merkle tree is public, and these proofs actually involve proving that you are spending a serial number without actually revealing the serial number, and proving that it's valid by proving that you know the path in a Merkle tree which has this coin commitment as a leaf, and the root of the Merkle tree is public. I don't want to get into details of Zcash, but what I want to do is look at another application on the blockchain which needs us to prove things about composite statements. So what do I mean? Let's look at the current approaches to practical zero knowledge. So this is in no way exhaustive, and it is a sampling that is going to serve the rest of my talk, but whatever I'm going to say is going to be true about even the schemes that I don't mention here. So if we look at approaches to practical zero knowledge, we have algebraic techniques like sigma protocols that work well in the sense that the prover and the verifier need to do only a constant number of exponentiations, and the proofs are small. And we have what I'm going to call non-algebraic techniques based on garbled circuits and MPC in the head and SNARKs and other things that I'm not mentioning here, which work well for statements that are expressed as a circuit. So of course, one can use either techniques to prove either statement. But what I mean by an algebraic statement is a statement like the following. If I want to prove knowledge of discrete logarithm of a public value, that's an algebraic statement and a sigma protocol works well. On the other hand, if I want to prove knowledge of pre-image of a hash function like SHA for a public value y, this lends itself to non-algebraic techniques. If we were to use, say, algebraic technique to prove a non-algebraic statement, this means that we have to write each gate in the circuit as an algebraic relation between the input wires and output wires, and use, for instance, a sigma protocol for every such algebraic relation. And this means the prover complexity and the proof size will grow with the size of the circuit, which is clearly undesirable. On the other hand, if we were to use a non-algebraic technique to prove an algebraic statement, we have to first represent an algebraic statement as a circuit. And n-bit modular exponentiation, for instance, is already a circuit that is cubic in the bit size of the modulus. So this blows up the size of the circuit, which increases the prover complexity in all these proof systems. So how do we prove composite statements? And by composite statements, I mean a combination statement that consists of both algebraic and non-algebraic components. And such statements come up frequently in practice. And one example I'll be talking about today is for privacy preserving audits on the blockchain. So we have the Bitcoin network, and most Bitcoin users transact via what are exchanges like Coinbase and BitX and so on. And these exchanges more or less work like online banks where users can create accounts, buy Bitcoins, sell Bitcoins, convert Bitcoins to altcoins or fiat currency and so on. While this is very convenient, it also leaves the users vulnerable to loss of coins when exchanges incur losses. Famously, Mt. Gox, which was one of the leading exchanges until a few years ago, and handled about 70% of all Bitcoin transactions, filed for bankruptcy after losing about $450 million in customer money. So the lesson here that exchanges have to be audited frequently and be asked to prove that they are actually solvent. And what does being solvent mean? It just means that the exchange controls enough assets to cover each of its customers' balances. So if everything was public, if the exchange was willing to publicly post the addresses that it controls and the corresponding assets and a list of its customers and their corresponding balances, we could simply publicly compute the total assets of the exchange and the total liabilities of the exchange and make sure that it is indeed solvent. But what about privacy? So the concerns typically are that the exchange doesn't want to reveal its total holdings because this is sensitive commercial information, and the users don't want their holdings to be revealed either because that is private. So can we have a proof of solvency where we can actually audit exchanges but in a privacy preserving way? So if we want to do this in a privacy preserving way, if the exchange were to prove its total assets, then we need the exchange to prove that it is only including those assets that it actually controls. That is, only those addresses are included in computing the assets for which it knows the corresponding secret key. So we want the exchange to prove ownership of Bitcoin addresses. So what does it mean to prove ownership of a Bitcoin address, for instance? So Bitcoin address, roughly there is a public key private key pair where the public key is G to the X for a secret key X, and the address itself is a hash of the public key. So the Bitcoin address that is available on the blockchain is H, which is hash of Y. And now to be able to prove ownership of a public Bitcoin address, the statement to prove is knowledge of X and Y such that they are a well-formed key pair, that Y is G to the X, and hash of Y is indeed the public value H. So now notice here that proving knowledge of X and Y such that they are a well-formed key pair for a Bitcoin address is an algebraic statement that we want to prove using algebraic techniques, whereas the hash part of the statement is a non-algebraic statement and we want to be able to use non-algebraic techniques to prove this. So this is a composite statement, and what makes this a composite statement is the shared witness Y between the two parts of the statement. So can we get the best of both worlds? Can we use sigma protocols to prove the algebraic part and a non-algebraic technique to prove the non-algebraic part? So if we were to use a simple combination of two protocols, does this already work? It doesn't, because a cheating prover can simply use two different witnesses in the two parts of the statement without actually having a single witness for the entire combination statement. So if we look at this particular statement here, imagine a cheating prover who actually happens to know the public key that corresponds to a Bitcoin address H. So the prover knows H and Y, but the prover doesn't actually own the address, so he doesn't know the secret key that corresponds to Y. But if we were to use two different techniques separately, then the prover can simply choose its own key pair, X prime and Y prime, that has got nothing to do with H here, and then give a valid proof that it knows a valid key pair and another valid proof that it knows the pre-image of the public H. And this would convince a verifier when actually the prover is not the owner of the corresponding Bitcoin address. So such a naive combination does not work, and one of the challenges is to be able to bind the value that the prover uses in the algebraic protocol with the input to the non-algebraic protocol. And of course we want to be able to do this without having to prove large circuit statements using algebraic techniques, and without using non-algebraic techniques for algebraic operations like exponentiation. So the state of the art, it's not state of the art now, but the prior work for privacy preserving proof of solvency called provisions was based on sigma protocol proofs. But like we saw, it doesn't really solve the Bitcoin problem, because in provisions the assumption was that the public keys themselves are available on the blockchain. And now what we have to prove is actually a simple algebraic statement where sigma protocols work. But the problem really is that the public keys are not available on the blockchain and only hashes of them are available. And prior work that gave constructions to combine algebraic and non-algebraic techniques were based on sigma protocols combined with garbled circuit based protocol. But this is inherently interactive because the garbled circuit based protocol, the verifier uses private coins, and it's not clear how to make it non-interactive. So again, this will not work for the blockchain setting. So the question really is, can we construct efficient non-interactive proofs for proving such composite statements? So towards such a construction, what we will do is build some tools and then put them together to obtain an efficient NIZK. We will first, I'll show some high-level ideas to get SNARK on algebraically committed inputs and outputs, and sigma protocols on committed output. And then these two tools and some other standard sigma protocols will allow us to obtain composition of algebraic and arithmetic representation of statements. For example, the statement here, where each of these Fi can have an efficient arithmetic or algebraic representation and can have shared secret inputs. So let's begin with SNARK on algebraically committed input and output. And this is a refresher slide for Pinocchio kind of zkSNARK that we saw, which are publicly verifiable and the most efficient today in terms of proof size. So recall we have in the CRS things in the exponent that are evaluations of the QAP polynomials at a secret point. And the proof itself consists of encodings of certain polynomials, including the quotient polynomial. And verification of the proof is checking divisibility using the bilinear map. So now to obtain a SNARK on algebraically committed input, the high-level idea is to separate the circuit wires into wires that correspond to input that we want committed to, and the rest of the intermediate wire values. So recall again, we have these encoded values in the exponent that the prover is going to compute as part of the proof. And now some of these AI values correspond to the committed input that we want to separate out. So now the prover is going to compute two different proof elements instead of just one, where VCOM is a linear combination of the VI polynomials, but only for those indices that correspond to committed input, and V mid is the rest of the coefficients. And now this does not mess with the divisibility check, because there is a way to still combine VCOM and V mid polynomials into the polynomial V. And together with some additional checks to ensure that the prover uses the same coefficient in the linear combination of these polynomials, we need to add certain additional CRS elements for the test to go through. But this is the high-level idea for how to get SNARK on committed input. But we separated the wires, but what did we do with the committed input? So now we notice that one of the proof elements, that is the element that encodes the VCOM polynomial, actually already looks like an algebraic commitment, where the base, that is G to the Vi of S, is already part of the CRS. So when I say algebraic commitment, I'm thinking about Peterson-like commitments. And now this is a simple standard sigma protocol proof to prove knowledge of exponents of a multi-exponentiation and a Peterson commitment, which we know how to do efficiently. And this proof binds the algebraic commitment and the input to the circuit that the prover used for the SNARK proof. We can also obtain sigma protocols on committed output using very similar techniques and including additional CRS elements, additional SNARK proof, and some other standard sigma protocol proofs to bind the values on the output wire with the values that are committed to inside a predestined commitment. And that gives us SNARK on algebraically committed input and output. And now what we want to do is bind these committed values to the values that's used in a sigma protocol. And for certain kinds of composition, what we actually want is a sigma protocol on committed output. So what do I mean? So one of the important tools that we will use in building a sigma protocol for committed output is the CDS OR transform for sigma protocols, which basically allows us to prove that either x0 is in the language or x1 is in the language, but without revealing which of the clauses was true. And the size of the proof grows with the number of clauses, but the prover, verifier, and concrete proof size still remains efficient. So now let's consider an algebraic statement with a 1-bit output. For instance, we want a sigma protocol to prove that f of xy is b, where y is public but x and b are only committed to. And using the CDS OR transform, so this is the statement we want to prove, that f of xy is b and c is the correct commitment to the same x that was used here, and b is the value inside the public commitment d. And we can do this by directly using the OR transform, where we prove that f of xy is 1 and the bit b is 1 using the standard sigma protocol for f, or b was 0 and d is indeed a commitment to 0. So this sort of gives us sigma protocols on committed output when we only care about the 1-bit output. But there are composite statements where we want to use the sigma protocol output as an intermediate state for the next SNARK, and there we actually care about committed outputs where things are group elements. For example, let's consider the statement here where the prover is proving knowledge of xi's and y, where y is basically so we are only given commitments to xi and y. So this notation, when I put things in parentheses, they are all witnesses and they are all secret, and the rest of the values are public. So given only commitments to all the xi's and commitment to y, we want to prove that y satisfies this relation where pi's are public polynomials. And the simplest instance of such a statement is when we only have one x and we want to prove that y is g to the x, except that y is not public. So we have commitments to x and y and we want to prove y is g to the x. And again, for the Bitcoin example and other applications too, these are generators of an elliptic curve group for reasons of efficiency. So what we need is a double discrete logarithm proof, which is known for integer groups but not for elliptic curve groups. So a starting point to build a proof like this for elliptic curve groups is a proof of point addition. So in elliptic curve groups, the group operation is point addition. And let's look at what point addition is. So a point addition is specified by an equation that is specific to the curve. And for the Bitcoin curve, it looks like this. So P and Q are points with x and y coordinates. And T is P plus Q, which is another point on the curve. And point addition is given by these equations where these specifies the add formula. And when P is equal to Q, there is a double formula, but essentially there is a public polynomial. In general, we can think of polynomials Lx and Rx between the two coordinates and Ly and Ry for the y coordinates that specify how to add points. And now, can we simply use sigma protocols to prove things about committed coordinates? of elliptic curve group points. That is the high level idea, but we run into technicality. The problem is the point addition computation is over Ft, where Ft is the scalar field over which the elliptic curve is defined, and commitments are in a group of order T, which is not necessarily the same as P, the order of the elliptic curve group. So there are two fields here, the scalar field that underlies the elliptic curve itself and the field over which we have the statement that we are trying to prove. And point addition itself is on the scalar field of the elliptic curve group, and there is a mismatch between this and the order of the group that we want. So what we want to do is to work in two different groups, G1 and G2, where G1 is the group of order P that we want, and we are going to choose G2 with order Q that is large enough to prevent wraparound by looking at the largest intermediate value in the point addition computation that shows up. And then we are going to commit to all the coordinates and the intermediate values in the second group of order Q, and then use sigma protocols to prove that point addition is satisfied. And now this proof, when we use a sigma protocol, is going to be equality mod Q, and we want to translate this into equality mod T, which is where we want the point addition computation to hold. And we can do this with division with remainder and additional proofs to check equality of remainders, and range proofs to check that the quotient and the remainder are in the correct interval. Okay, so with this we can show that given 2 points, P is not Q and not minus Q, and a committed value satisfies the add formula, or P is indeed equal to Q and the double formula is satisfied, or that P is minus Q and T is indeed 0. And this is again using the OR transform, so we don't reveal anything about which clause is satisfied. Okay, so now we are ready to build a double discrete logarithm proof in elliptic curve groups. So what we want to prove is T is P to the lambda, where we are only given commitments to T and lambda, and P is public. So C1 is a commitment to lambda in a group of order P. Remember, T is a point on the curve, which means there are 2 coordinates, and when I write commitment, I really mean 2 commitments to both the x and y coordinates in a group of order Q. The prover chooses a random alpha, computes Q as P to the alpha, and sends out commitments to alpha and Q. The verifier sends a challenge bit, 0 or 1. And if the challenge is 0, the prover is going to just reveal the random alpha here. If the challenge is 1, the prover is going to compute Z as the difference between alpha and lambda, and in addition give a proof that this point addition is satisfied. So I'm using multiplicative notation here, but this is really point addition in elliptic curve groups. The verifier is going to verify the commitments and the proof pi, and to prove that P to the Z is indeed Q T inverse, we use the point addition proof that I just talked about. There has been more work on NIZK for composite statements. There is this work called zkSNARK by Dario Fior and others, where they show a modular way to construct what they call a commit and prove SNARK, so that SNARKs can maintain intermediate states, and there are ways to put SNARKs together on committed values. There is this other work that shows how to combine sigma protocols with MPC in the head approach, zkBoo. But this is not directly applicable because this still results in proofs that are larger than we want. Okay, so now that we have techniques for NIZK on composite statements, we can go back and solve our proof of solvency problem. So remember, there are all these Bitcoin addresses, corresponding balances, and a liability table that lists customers and their corresponding balances. So now what the high level idea for what the exchange should do is to compute a commitment to the total assets and a commitment to its total liabilities. And then we use a homomorphic commitment scheme, and we can check that the commitment here is 0, or the assets covers the liabilities to some acceptable degree. So for a proof of assets, so the exchange actually controls some private keys for a subset of the Bitcoin addresses, and it wants to commit to the total value at these addresses. So it's going to pick some of the hash values on the blockchain to serve as the anonymity set. And for the private keys that it actually owns, it's going to commit to the balance. And for the rest of the addresses in the anonymity set for which it does not know the private key, the exchange commits to 0. So these are going to be commitments to 0 for addresses not controlled in the anonymity set. And now for each address in the anonymity set, the exchange gives out a proof that basically says, I know the secret key that corresponds to the public key, and the commitment is to the correct balance, or I commit it to 0. So if we look at what this proof looks like, so there is a proof per address that is included in the anonymity set. So the size of the proof grows with the size of the anonymity set. And there are commitments to xi and yi, which are the private and public keys of the address, and hi is publicly known. And commitment to bi for an address that is controlled, and commitment to 0 for an address not controlled. And now the proof is going to be that this is a valid key pair, and the hash corresponds to the correct public hash, and bi is the correct balance, or bi is 0. And for doing this, we use the double discrete logarithm proof that we saw, where yi and xi are only committed to, and we want to prove the correct relationship. For the non-algebraic part of the statement, we are going to use SNARK on committed input, which also we just saw. And this commitment ties the y here with the y in the double discrete logarithm proof. And finally, this is going to be the standard CDS or transform. So the proof hides which address is actually controlled and which ones are not. Okay, so the proof of assets is going to be one such proof for every address that is included in the anonymity set. And now we have a commitment to the total assets that the exchange controls. So one can homomorphically compute this commitment to the total assets of the exchange. And now we also need a proof of liabilities, which includes what the exchange owes to each of its customer. And this is done by including one entry in the liability list for every customer. So there is a customer ID for every customer and a commitment to the balance of that customer. And each customer is going to verify that his or her balance is actually included in the list. And now we also want that each committed balance in the liability list only adds to the liability. So we also want to check that these committed values are in the correct range. And for this, we'll need a SNARK on committed input again. So a proof of liability includes these range proofs for each entry in the liability list. And given homomorphic commitments, we can again homomorphically compute a commitment to the total liability of the exchange. And a proof of solvency given both these commitments is to simply compute a commitment to the balance and prove that it is 0 or a surplus exists if need be. Okay. I want to just briefly mention another setting for an application where composite statements show up, and I'm going to talk about this a little bit more in the next talk. So privacy preserving credentials, we have the following setting where we have a certificate authority or an organization, and a user who is going to obtain credentials from this organization and later wants to be able to use it to prove certain properties to a service provider or a merchant. So the organization issues certain credentials which basically certifies the user's name and address and citizenship and so on. And the user here later wants to prove to a verifier that he's old enough to vote or a resident of a particular state and so on. So the user can of course use the credentials he got from the CA, but this would unfortunately reveal more information than necessary. So this is not what we want. We instead want a way for the user to be able to prove to Alice using the credentials that his credentials satisfy a certain policy. And the policy can be as granular as the application dictates. So anonymous credentials have been studied and has a rich history beginning from the work of Chaum. And most practical credential systems like Microsoft's uProve and IBM's IDMX follow a rather standard template. So the high level idea is the credential itself is a signature of the organization on the user's attributes. And to be able to prove possession of attributes, the user proves in zero knowledge of signature on committed attributes, and then proves again in zero knowledge that the committed attributes satisfy a certain policy. Now what this means is for the user to be able to give an efficient sigma protocol proof, the signature has to be specially formed to allow a sigma protocol for proof of knowledge of signature on a committed value. And what if we want to base credentials on standard signatures? So what if the CA wants to use off-the-shelf signatures? Or if the user is already in possession of a standard signature and wants to use it in a privacy-preserving way? So if we want to base anonymous credentials on standard signatures, for instance, if we look at RSA signature, which looks like this, where the signature is hash of the message to the secret key mod n, verification involves checking that hash of the message is sigma to the e mod n. And this verification again involves both exponentiation in an RSA group and computing a hash function, which we want to do efficiently using techniques for composite statement. So a very high level idea of how to do this using the kind of techniques we just saw is to commit to the hash h, the message and the signature, and then give a SNARK proof on committed input and output where m and h are witnesses such that hash of m is h and C2 and C1 are indeed commitments to the message and the hash of the message. And then give a proof of knowledge of eth root of the committed value, which is a standard sigma protocol that we know how to do. And finally, these two proofs are going to be commitments in groups of different kinds and orders, where this is a SNARK friendly group and this is going to be an RSA group, so we need more tools to show equality of committed values across groups of different order, which we know how to do, but I'm not going to get into it. Okay, so let's get back to the setting of preprocessing SNARKs. And I want to say a little bit about this whole setup phase. So recall we have this really short proof and efficient verification, but all this is assuming that we have a setup phase where some coins were tossed and we got this proving and verification key, which allowed us to obtain really short proofs. So in practice, we have to ask who sets up these keys? And why do we have to trust the setup? Do we have to trust the setup? Can things go wrong if the setup is corrupt? And these are arguments, which means proofs for false statements exist, it's just not efficient to find them. And indeed, if the setup is corrupt, one can efficiently prove false statements. So in these preprocessing SNARKs, there is a trapdoor that is associated with the CRS that allows a corrupt setup who is in possession of this trapdoor to break integrity. That is, one can prove false statements if the setup actually remembered how these parameters were sampled. So when assuming a trusted setup, we are basically saying a party is going to sample some parameters and then delete the randomness, and we have to believe that party. And in practice, this can be unreasonable. So one way to mitigate this is to replace this one party with many parties who compute the setup function. And a group of people are going to compute exactly what one party would do, and we replace this with a multi-party computation. But this is still a mitigation because of two reasons. So again, remember, these are the kind of SNARKs that actually underlie Zcash, and real money is at stake here. So Zcash actually ran a trusted setup ceremony. And after the trusted setup ceremony, if the trapdoor was not disposed of properly, breaking integrity of the proof system actually means some people who have the trapdoor can print money at will. And in addition, there is no easy way to determine if a setup was actually compromised or not. And the second issue is that the trusted setup gives us an output that allows us to prove things for a circuit that it was designed for. And for every application, we need to run a different trusted setup, which not only adds to the overhead, it also means less scrutiny is given to each ceremony as we have more and more trusted setups when we expect these proofs to be deployed at a wider scale. Recently this issue of trusted setup has got some attention, and one alternative is to just use transparent SNARKs where parameters are unstructured and the randomness involved is public. But they still don't give us concretely efficient proofs comparable to preprocessing based SNARKs. An alternative model that allows us to minimize the degree of trust we put in the setup phase while also retaining the advantages of proof size and verification in preprocessing based SNARKs is this model called Updatable Common Reference String SNARKs, proposed by Groth, Kohlweiss, Meiklejohn, Mahler, and Myers. So what this says is the following. So imagine we have a setup phase that gives us some CRS, and now some party comes along and he doesn't trust this CRS to be not backdoored. So it can sample its own randomness and update the CRS and obtain a new CRS. Another party can come along, sample its own randomness, perform an update again and obtain a different CRS. And so we can continue to add more parties to the update phase. So this no longer looks like a traditional setup. So it's not a one-time setup. This update can be continued and parties can be added. And the guarantee we get is that a CRS is secure at any point after one honest user has updated. If we are willing to trust that one of these users disposed of their trapdoor correctly, then after that user's update, we have a good CRS that we can trust. Yeah. Yes, yeah. So the proving and the verification is with respect to the latest CRS, and everybody has to agree on which CRS they are using. No. We have to assume it should be correct, but not that it is backdoorless. We don't have to assume anything about. Exactly.
Then you're confused about how things keep updating and how do we know, like, if you have proof in the past, you have to kind of keep track of all previous versions.
So what I didn't say here is there are these update proofs that actually talk about which CRS or derived CRS came from, but these update proofs are short. There are a few group elements, but of course it grows with every update we make. This is of course not the best solution, and I'll get to state-of-the-art updatable CRS in one slide. Right, so what Groth et al. Show in this first updatable CRS model is both a negative and a positive result. So if we remember, in GGPR kind of preprocessing SNARKs, there are secret exponents in the CRS. And these exponents are actually evaluations of the QAP polynomials. They were terms like this, which were put in the exponent. And if we think about monomials in the exponent, it's easy to see that they can indeed be updated. So let's say we have a monomial x in the exponent. Now any party can update it, give a proof of knowledge of x1. Another party can sample its own x2, update it to g to the x1, x2, and give a proof of knowledge of x2, and so on. So monomials, we know how to update, it's easy. And we know SNARKs where the CRS only consists of monomial evaluations. These are constructions that precede GGPR. These are works of Groth and Lipma. But the downside is that they have inefficient provers. The prover is quadratic in the size of the circuit that we want to prove, whereas in GGPR kind of proofs, the prover is quasi-linear. But the compilation from the information theoretic object means the CRS has evaluations of all corresponding polynomials. And somehow what that means is, so in GGPR, when we only have CRS that contains polynomial evaluations, updatability would also mean that the adversary has to know all the monomial evaluations. And that is sufficient to break soundness of Pinocchio and even GGPR. Monomials we know how to update efficiently, and we also know constructions that only have monomials in the CRS, but they're not efficient for proving. What Groth et al. Show is that a CRS that contains polynomial evaluations of a secret cannot be updated. If it were updatable, then there is a monomial extractor that can also extract evaluations of all the involved monomials, and that already breaks soundness. The positive result is the following. They have what is called a global CRS, and this global CRS is independent of the circuit that we want to prove. And again, anybody can update this global CRS, and at the end of the update, once you're happy that some update is good, we can publicly derive a circuit-specific CRS. And this circuit-specific CRS embeds a circuit-dependent QAP, and this can be used to prove a fixed relation. What are the trade-offs? So we now have an updatable CRS SNARK that gives us short proofs. Proofs are still as short as GGPR. But now what happens is the global CRS is quadratic in size, and the derive algorithm itself is cubic in the number of gates in the circuit. The circuit-specific CRS is still linear. But if we look at just the kind of statements that arise in Zcash, this is already a lot of overhead. The CRS is too big, and the derive is, the overhead is too much, and we lose a lot in efficiency. So the idea is we start with a large global CRS, and this global CRS is updatable. And from this global CRS, we can derive a smaller CRS, and this derive can be run by any party. And the derived CRS is sort of equivalent to the setup of all previous QAP-based schemes. In recent works, starting from Sonic, they consider a constraint system that bypasses the QAP. So they write down the arithmetic circuit and write a set of constraints that already capture the circuit constraints, and then go from this constraint system to a zkSNARK, which has several advantages. When compared to the Groth et al. Scheme, Sonic has an updatable CRS, which is just linear in size. So the global CRS is not quadratic anymore. And moreover, there is no derive. There is no circuit-specific CRS. There is only one CRS, which is constantly updatable. And the proof sizes are longer than Groth et al., but still constant. It's like 16 group elements or something. And I just want to talk about this important building block that is used in Sonic and Marlin and all the other recent zkSNARKs, which is a polynomial commitment scheme, where a prover has a polynomial and wants to commit to the polynomial so that later, when challenged on a particular point, it can open the polynomial at that point together with a proof. Given any commitment scheme, of course, we can commit to the polynomial by committing to each of these coefficients independently. But what we want is a succinct polynomial commitment scheme where this commitment is independent of the degree of the polynomial. And this is an essential building block for SONIC and all subsequent works, where the idea is to represent circuit constraints as constraints about polynomials, and then use a polynomial commitment scheme to commit to the polynomial. And this allows not only an updatable CRS, but a universal CRS, where we don't have to know the circuit that we want to prove in advance. I just want to end by saying there are plenty of applications for Succinct zkSNARKs. Blockchains are a wonderful use case because we want both short proofs and efficient verification. Disclaimer, the pace of progress is so much that inevitably there have been omissions. There are plenty of other proof systems that offer various trade-offs based on different assumptions. There are STARKs, bullet proofs, which are only based on discrete log assumptions, though they don't give really short proofs. Proof sizes are logarithmic. There is supersonic, Halo, and a line of work that I didn't talk about at all called Libra and Virgo based on GKR style proofs. And plenty of open questions. I'll just leave the slide here, and I'm happy to take questions. Thank you.